Okay, so let's do a combined loading problem. What we're going to do is we're going to try to figure out what the stress state is at this point C. So we got this set up here. Draw a quick free body diagram. One of these days I'm going to learn how to draw a straight line on this thing. So again, we've got this distributed force. That distributed force, if we want to represent it as a resultant, let's do that. So it's 2.5 meters in length, and it's distributed over 50 kilonewton. Sorry, and it's a 50 kilonewton per meter distribution. So that gives us 125 kilonewtons, and of course that'll be kind of located 1.25 meters from there. We're going to have a reaction in Y at A. We're going to have a reaction in X of A. And we're going to have a reaction at B. So the directionality of the reaction at B. So again, we know that B is going to be acting perpendicular to this slope here. So again, this slope here is defined by this triangle, 1.5 meters, 2 meters, 2.5 meters. Multiply by that by 2, we get a 3, 4, 5 triangle, which means that the triangle that's perpendicular to that is also a 3, 4, 5 triangle, just switching which one's in the Y and the X direction. So our BY is going to equal to B times 4 over 5. Our BX is going to be equal to B times 3 over 5. Okay, so similarly, we may want to let's go ahead and break up the 125 kilonewton force into its x and y components. So 125 kilonewtons. Again, it's acting parallel but opposite directions to B there. So times 4 over 5 gives us, that's 100 kilonewtons. So that's the y component. And then we're also going to get an x component. 125 times 3 over 5. That's 75 kilonewtons. So let's go ahead and take a moment about A to try to figure out what B is. So sum of moments about A is equal to 0, which is equal to, so if we have our the 125 kilonewton force kind of broken up into its x and y components. Let's see, what do we have here? So we know it's going to be acting at a point that's right here. Right here. So that'll be its vertical distance from A will be 0.75. And its horizontal distance will be 1 meter plus the 4 meters, so 5 meters. So the downward portion of that force is going to be causing a negative moment, because again, that's going to be a clockwise rotation when we take in about A, when we push down on it. So negative 100 kilonewtons times its horizontal displacement, which is 5 meters. And then we also have the horizontal portion of that. It's also acting in a, it's also going to be, if we push this way, that's clockwise about A, so that'll be a negative moment as well. So negative 75 kilonewtons times the vertical displacement there is 0.175 meters. And then we have the reactions at B. So the reaction, the BY portion, again, that'll be pushing up. That's a positive moment about A. So that'll be BY times the 6 meter span horizontal. So plus 6 meters BY, but I'm not going to put BY down. I'm going to put B times 4 over 5. 4 over 5 B. And we have the horizontal portion. Again, that's also clockwise rotation. Oh, sorry, also a counterclockwise rotation. So it's also a positive moment. And its vertical displacement there is the 1.5 meters. Oh, I forgot to put the meters here. 1.5 meters times, again, bx is b times 3 over 5. So we can use that to solve for b. So let's see here. What do we have for b first? So 6 times 4 divided by 5 plus 1.5 times 3 over 5. That gives us 5.7 B. 5.7 meters B. And this grouping here, so that's these terms here combined. This grouping here, 100 kilonewtons times 5 meters, and 75 kilonewtons times 0.75 meters. So that'll be, both those terms are negative. So we end up with 0 is equal to negative 556.25 kilonewton meters plus 5.7 meters B. So based upon that, we can solve for B by dividing the 556 by 5.7 meters. So that'll give us 97.59 kilonewtons. Alright, so that's what B is. I'm going to want to re-break that up into its x and y components. So by is equal to 4 over 5 B, which is equal to, that times 0.8 is 78.07 kilonewtons. Bx, on the other hand, that's equal to 3 over 5 B, which is equal to 55 kilonewtons. Okay, so we got those. Now we can use that to solve for our reactions at A. So again, just looking at this, sum of the forces in the y direction. One of these days I'm going to be able to draw a sigma without it looking terrible, but not today. Some force of y direction is equal to 0, so that's going to be equal to ay plus 78.07 kilonewtons minus the y portion of the load, so minus 100 kilonewtons. So solving for ay, we get 100 minus 78.07. That gives us an ay is equal to 21.93 kilonewtons. And then we have our sum of the forces. Hey, that wasn't too terrible. And the x is equal to 0, so that's going to be equal to ax and minus the 75 kilonewtons. That's the horizontal component of the distributed load. And then bx is acting in the positive x direction. So 75 minus, solving for what ay gives us 75 minus 58.55. So ay is equal to 16.45 kilonewtons. Okay, so I'll just do a quick redraw. Okay, so we got 16.45. We got 21.9293. Got the distributed load. And then we got B, so 97.59. Kilonewton, that was 50 kilonewtons per meter. Okay, so we are worried about point C. Right here, point C is located, come on OneNote, show me the rest of the drawing. Anytime now. Point C is located 1.5 meters away from the joint there. So we can. So basically, when we draw, let's do a shear diagram for just this section right here. So just for that section right there, we are pushing up. We're pushing up and on the left, so we start out with a positive 21, and then and then it turns a corner and weird stuff happens, and I'm not too worried about that because I'm not worried about what happens around that corner. So at the point that we're worried about, the shear is going to be 21.93 kilonewtons. And we can also use that to draw a moment diagram. In the area in question, starts at 0, increases linearly at a rate of 21.93 kilonewtons. So at the point C, which is again 1.5 meters away, our moment will have grown to 32 point, let's call this C. Oh, we'll put C there. Put C there. So 32.9895 kilonewton meters. I'll just put that 32.9. And we can also do a normal force diagram for that section because we are pushing on it. So we're pushing on it, so it's actually negative. So it'll be throughout that section, it will be a constant negative 16.2. Was it 25? 45. 16.45 kilonewtons. So those are the loads that we're worried about. There's not going to be any torque. So just the cross section is 250 millimeters by 50 millimeters. So 250 by 50. So let's figure out some properties. The area there, 250 by 50 gives us 12,500 millimeters squared. Our I, so again, neutral axis is going to be there. Our I is going to be 250 millimeters cubed times 50 millimeters divided by oh, sorry, I just realized I was kind of drawing under my head there in the recording. Divided by 12. So 250 to the third times 50 divided by 12. That gives us 65.1 times 10 to the 6 millimeters to the fourth. Okay, so stresses. What sort of stresses are we going to be having here? So the location of the points that we're worried about, that was given as, I'm going to put it in pink here, that was given right there. So while there is a shear load in this section, at that point, the Q is going to be equal to 0 because the area that is kind of separated from the neutral axis by a section through that point is 0. So at the top corner there, we don't have any shear stress. We only have the axial stresses. So we have a positive bending moment there. So that means, when we calculate our bending stress, negative my over I. So our bending moment there is 32.9 kilonewton meters. And I'm going to want to put that in terms of Newton meters. So times 1,000 millimeters per meter. Oh, actually, sorry, I accidentally put millimeters instead of meters when I drew that here. But those meters cancel out, and then just times 1,000 for the newtons per kilonewton. So we got that. Got our y, so our y is the distance from here to here, so that'll be 125 millimeters, and then all that over the 65.1 times 10 to the 6 millimeters to the fourth. So again, these millimeters cancel out with 2 of these millimeters, and then we're left with units of newtons per millimeter squared, which is a megapascal. So 32.9 times 1,000 times 1,000 times 125 divided by 65.1 million gives us a bending stress. Oh, forgot the negative there. Bending stress of negative 63.2 megapascals. So this is not exactly surprising at all. Yeah, it's a reasonably large value, but not out of the ordinary. So we got that, and we're also going to need to combine that with the axial stress. Normal stress, I'll call it normal stress. No, axial. Yeah, whatever. So that's just P over A. So the load in this case, that's the 16.45 kilonewtons. Again, it's a compressive load, so negative 16.45 times 1,000 newtons divided by our area. So 12,500 millimeters squared. Newtons per millimeter squared gives us megapascals. So we are at 16.45 divided times 1,000 divided by 12,500. That gives us negative 1.32 megapascals. So the stress state at C is just the combination of those two. And that'll be based upon our original coordinate system. That'll be in the x direction. So our total stress state both those are negative, so they combine to negative 64.5. At that point, all our other stresses are 0. And that is about that.